Welcome back. We're now going to move on to our conversation about horizontal asymptotes. So we've already talked about vertical asymptotes, and now we're going to move on to the concept of horizontal asymptote. So if you look at those same graphs as before, you'll notice right now I have f of x, it's the first one, and then of course my favorite, the j of x is pulled up right now. So if you look at those graphs, you'll notice that, yes, they're broken apart, and we have the vertical asymptote to thank for that, but they also seem to have a horizontally running barrier through them as well. So like for instance, if I focus on just the f of x graph, they break apart at -8 because vertical asymptote is at x equals -8, but horizontally speaking, check it out. They also seem to flatten out, if you will, and approach a horizontal barrier as well. It's not like these graphs just go, up and down and fluctuate and do all sorts of crazy things like polynomials did. This graph, if you look at it in the long run, it levels out. Now, this particular graph seems to level out at the x-axis, so we'll talk about that. But j of x, my favorite purple one, j of x also levels out eventually. Don't get me wrong, it does all sorts of crazy fun stuff in the middle, but eventually it does seem to level out. It levels out on the right-hand side, and it also levels out on the left-hand side. Now, the number, though, that it levels out to, it's not the x-axis this time. It's something a little higher than the x-axis. If I just had to like run my eyeballs through there, it's somewhere around like 2 or 3. It's not the x-axis. The first graph seems to level out at the x-axis, but this other graph does not. Levels out, yes, but not at the x-axis. So the horizontal asymptote conversation, ladies and gents, is not a conversation of errors. Nope. It's a conversation of what the graph does in the, we call it in the long run, or in the end behavior of the function. The horizontal asymptote is what the graph does, how the graph behaves in the quote long run, or in its end behavior. Now, once again, the reason we had to do polynomials first is because the end behavior of a rational function is tied to the end behavior of polynomials. Remember, a rational function is just the division of 2 polynomials. So if we look at these functions and ask ourselves what's happening with the polynomials that are on top and bottom, that's when you'll get a sense for what the horizontal asymptotes are doing. Okay, so this is divided up into 3 cases. So case 1 involves us looking specifically at that first graph, the f of x equals 10 over x plus 8, and also graph h of x. These both go under case 1, and you'll see why they go together in a second. Okay, so when we're talking horizontal asymptote, once again, we are not talking about errors. We're talking about the end behavior. And whenever we say end behavior, we mean that x is going towards either positive infinity or negative infinity, but nonetheless, way out there, way out there. So if you think about what this function is doing as x gets really, 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 really big, well, on top it would still just be a 10 because there's not even an x on top to be affected by this conversation. And on the bottom, it would be something really, really, really big plus 8. Now, in the scheme of things, the plus 8 is pretty insignificant. What you have essentially in front of you is that it's 10 divided by something huge. Okay, guys, think with me here. What is 10 divided by huge? Practically nothing. 10 divided by huge is pretty much 0. So as you plug in numbers that are bigger and bigger and bigger and bigger and bigger, the 10 is just a 10 because there's no x on top. The denominator, on the other hand, does have an x. So it gets bigger and bigger and bigger and bigger. And so this particular graph in the long run, or in its end behavior, is going to be practically nothing, which is why this particular graph leveled out at the x-axis. A y value of 0, yeah, that's the x-axis. So as this graph went on and on and on and on and on and on, the answers, the outputs, got smaller and 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 smaller, pretty much nothing. It doesn't ever actually reach 0 because technically 10 divided by cajillion is 0.00000000000000001. So it's not actually 0, but it approaches that 0 line. Now check out this next one for the h of x. As x goes to infinity on this one, you would have essentially -2 copies of infinity plus 5 over 4 copies of infinity squared plus 16. Okay, well, here's where the discussion of polynomials and end behavior comes in. When you're talking about polynomial functions, everything is driven by the degree of the polynomial. The degree, remember that? The highest exponent in the formula is called the degree. So this numerator is degree 1 because it was -2x, that's x to the first. The denominator is degree 2, it's squared, it's quadratic on the bottom. So in the grand scheme of things, anything else is not as significant as whatever the degrees coefficient is. The meat and potatoes of how a polynomial acts is based on its degree. So these polynomials are essentially going to act like just -2x and 4x squared. And yes, you're imagining what would happen if x got really, 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 really big. Well, with regards to these variables, once you focus on just those, do you realize that you can reduce out one of these x's? So like what this is the same as saying is 2x over 4x times x, right? X squared is x times x. So one of those x's can reduce out. They just divide each other out. So what you end up really having to focus on is 2 over 4x. In terms of the degree, that's what it would all kind of amount to. Okay, but again, we're talking end behavior right now. So you are now imagining that x value getting really, 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 really big. Well, okay, guys, what's 2 divided by 4 cajillion? Not a trick question. What is 2 divided by 4 cajillion? Practically nothing. If you think about what would happen to these polynomials as x got bigger and bigger and bigger and bigger and bigger, the fact that you had a squared on the bottom means that there will always be that leftover x on the bottom, which means that the bottom will always be bigger. And if we're talking about a fraction that has a really, really, really big bottom, well, the answer for that is practically nothing. This graph, if we go back to it, should also level out at the x-axis, the 0 line. Let's go look. So that was h of x, h of x, h of x. So turn these ones off, h of x. Oh yeah, this was my one with a little blip. So remember, no vertical asymptotes, no breaks, just a little blip. But does this graph level out to the 0 line? Sure does. on the right-hand side, I'm just under the 0 line, negative 0.041. You see that? Just under the 0 line. And on this side, just over the 0 line. So this graph in the long run, way out here, levels out to the 0 line. So the horizontal asymptote is the 0 line on this function. And it was also the 0 line on this first one, the f of x. So both of those functions, my green and my blue, if you zoom way out, you can see that they both level out to that 0 line. That's why they both get lumped together in what I call case 1. Okay, let's go look at case 2. So case 2 involves the functions g of x. So and let's get a new color. Let's get blue. Okay. So g of x goes in case 2. That was 5x over 5x plus 4. And then the other one that goes in this category is j, my favorite one, j of x, which was the 3 times x minus 2, x plus 4, and then also x minus 4 times x plus 3. Okay. Now, remember, vertical asymptotes, those are errors. They come from the denominator equaling 0. Right now, we are talking about end behavior. So what would happen if x got really big? Okay, well, as far as polynomials go, they're driven by the degree. So the degree of the numerator is just linear. It's 5x. So it would be just that. And then the degree of the denominator is also just 1, degree 1. They're both degree 1. So this would be the strongest term on the bottom. Okay. Now there's 2 ways you can look at this. You can think of this as, well, the x's just divide out. And so really you just have 5 over 5, which is 1. Or you can imagine what would happen to these numbers if we imagine x getting really big. So what would happen if I plugged in something gargantuous on top and something gargantuous on the bottom? So if you think about it, the bottom is technically 5x plus 4. Don't get me wrong. I know there's a plus 4 down there. But in the grand scheme of things, on an infinitely large scale, the plus 4 is, it's pretty minute. If you're a cajillionaire and you find $4 on the floor, you're not that excited. You're already a cajillionaire. So we're focusing on the end behavior. The degree drives the end behavior. And this is not meant to be a trick question, guys. You ready? What's 5 cajillion divided by 5 cajillion? 5 cajillion divided by 5 cajillion is pretty much 1. And if you go back here, when we just focused on the leading terms, the degree terms, we said that the x's could divide each other out. And then you'd have 5 over 5, which is 1. So g of x in the long run, in the end behavior, seems to approach an output value of 1. We'll go back on the graph and we'll fact check that in a minute. But let's go look at j of x. Now, j of x is a little bit tricky because it's in factored form, but can you imagine with me here for a second that what you really have on top is a quadratic of sorts? You don't have to actually distribute it out to see that or to like fully simplify it, but nonetheless, what you have here, if you were to distribute, you have an x times x function. And specifically, you have a 3x times x function. Oh, that first bump, you wouldn't distribute the 3 twice. I'm sorry, that first little bump was wrong. You would have x times x, which is x squared, and then also 3 times that. So the top is going to end up acting like a 3x squared graph. Is there more to it? Yes, there is. But in its end behavior, it's going to be acting like a 3x squared graph. The bottom in its end behavior is going to be acting like the degree, a squared graph, x squared. Now again, I know there's more terms and those terms do have an effect, of course they do, but we're talking about the end behavior right now. And in the long run, these polynomials will act like their degrees. So now think about this, we'll do it both ways again. If you now imagine x is getting huge, 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 huge. All right. So now you've got 3 cajillions divided by 1 cajillion. Not a trick question. Think about it for a second. What is 3 cajillion divided by 1 cajillion? 3 cajillion divided by 1 cajillion is pretty much 3. And if you go back to the variable terms, we had 3x squared divided by x squared. Notice the x squareds essentially divide each other out, but that coefficient of 3 is certainly still there, 3 over 1 technically. So this graph should level out at an output value of 3, not the x-axis like the other ones did, but at 3. Let's go look at the graph and fact check that. All right, so these are off, and what do we got? G and J. Okay, so we said that the G of X graph, let me focus on that one first. We said that the G of X graph leveled out at 1, is that right? Well, let me put down here, Y equals 1. Check that out. Look at how perfectly the blue curve is just skating right along that purple line at 1. Yep, the horizontal asymptote, the approaching value is absolutely at 1. Because of that degree, that 5x over 5x, 5 over 5, it just reduces to 1. And then the other one, J of x, we said that that one leveled out to an output value of 3. Let me change that color for a second. There we go. Okay, so notice on this one, it doesn't level out in the middle. All this jazz, no, that is not leveling out. But if I zoom out, and if I look in the long run, the end behavior, check it out. It's totally hugging that 3. Yes, it is leveling out to 3. Yes, it is. And on the other side, follow it over, 2.85, 2.87. Oops, I lost my purple line. They got so dang overlapping. See what happens? There we go. Here's my purple line. Yes, it is leveling out to 3. Absolutely. So, end behavior. Does the curve level out in the middle? Not at all. But does the curve level out in the long run? Yes, it does. And where does it level out to? An output value of 3. So the horizontal asymptote for that curve is 3. Because the degrees on top, it was squared on top, squared on bottom, pretty much a wash. Squared over squared reduces out, but the coefficient of 3 is still there. And then last but not least, the last case is that last graph. Let me get my little whiteboard back. Here we go. So case number 3, the last one, is the only one we haven't done yet, and that is the K of x. So K of x is case 3, and K of x is x squared minus 2x plus 20, and divided by x minus 6. Okay, and we are talking about as x gets bigger and bigger and bigger and bigger. Okay, so as x gets bigger and bigger and bigger and bigger, this top polynomial is going to end up acting like a squared graph. You're going to see a parabola. Yes, it's got other components. It'll move the vertex, it'll shift it, it'll lift it up 20 units or whatever. But in the end, the degree is squared. So it's going to act like a squared graph. The denominator, x minus 6, okay, in the scheme of things, yeah, the minus 6 will shift it down 6. Yes, we know, but the degree is just a degree 1. x to the first, technically. So let's think about this two ways. First, think about it as plugging in. Technically, you can't plug in infinity, but just imagine with me here for a second that you had like infinity squared over just infinity. So you're taking something hugely big and also dividing it by something big. And you're like, well, I don't know. I mean, is big divided by big just a wash? I mean, kind of, but not really, because think about it this way. Infinity squared really means 2 copies of infinity. And yes, you're dividing it by the other infinity, don't get me wrong. But in terms of magnitude, the magnitude of the numerator is significantly bigger than the magnitude of the denominator. Whatever big number you're pretending to plug in right now, you've got twice as many copies of that on top as you do on the bottom. So one of those magnitudes could reduce out, but the other one is just still friggin' huge. The numerator is still huge. So in terms of what this one levels out to, I kind of feel like I'm just gonna still have a really big number. Now let's think about it in terms of just the powers. So x squared over x, also known as x times x divided by x. So in the same kind of conversation, or same reasoning, maybe I should say, you can see that one of those x's can divide out, but the other one is still there. And if you then imagine that that x is going to go towards infinity, well, the answer is just going to be freaking infinity. It's just really big. So on this particular one, I feel like the answer is infinity, which is strange. Let's go look at the graph and see if we can make sense of it. So the graph, we are talking about k of x, which is this one. Okay, so check this one out. Where does this graph level out to? So imagine you're driving your car and you're like, whee! And you just keep going, keep going. Are you leveling out right now? If you imagine yourself on this car ride, are you leveling out? No, you're just going up and up and up and up and up and up and up. You're not leveling out. What about in the other direction? So imagine driving your car along this curve and you're like, whee, going the other way. Okay, keep going, whee, keep going. Keep going. Are you leveling out right now? No. You're just going down and down and down and down and down. This graph does not level out. It doesn't. There is no leveling out value. There is no horizontal asymptote. This graph just shoots towards infinity. On the other side, it shoots towards negative infinity. Okay, fine, negative infinity or positive infinity, but either way, it doesn't level out. There is no horizontal asymptote. So as you see from our 3 cases, it all comes down to the degree. In case 1, you'll notice that you had the largest degree on the bottom. The largest degree term was on the bottom. In your first example, it was just 10 divided by x, so there was no degree on top, and then a degree of 1 on the bottom. So yeah, the bottom was heavier. And then on the other one, it was just an x to the first. H of x was x to the first on top, but x squared on the bottom. So the largest one was on the bottom. And anytime you've got the largest degree on the bottom, once again, think about a fraction that's really bottom heavy. So what's like 10 divided by huge? It's practically nothing. What's, 50 divided by gargantuous? Practically nothing. If your fraction is what I call bottom heavy, then your answer in the long run is going to be practically nothing. The horizontal asymptote, you're going to see that the graph levels out to the 0 line. That's case 1. Case 2, is when they were a match. Degree matches on top to bottom. So this one was like g of x. Remember, it was 5x over 5x, x to the first on top, also x to the first on the bottom. They're the same. Also j of x, it was squared on top, 3x squared, but it was also squared on the bottom. So it was squared over squared. Yeah, that's a match. So anytime it's a match, your horizontal asymptote ends up being whatever those coefficients are of those degrees. So remember with the 5x over 5x, the answer was 1. That's because 5 over 5 is 1. And then remember on j of x, it was 3 over 1, or it was, I guess, just 3. But that's because it was 3x squared on top and 1x squared on the bottom, and 3 over 1 is just 3. So this is the coefficient of the top degree, and this is the coefficient. Coefficient just means the number out in front. Coefficient of the bottom degree. Whatever those coefficients are, that will determine your asymptote, because as far as the powers are concerned, they're a wash. Like x over x, it's a wash. So focus on the coefficients, 5 over 5. X squared over x squared, that's a wash. So focus on the coefficients, it was 3 over 1. And then the last case, the one that we just did at the very end, the last case is case 3. That was the k of x. And that is, what if you are top heavy? So the degree is largest on top. That was the very last one. So imagine now that you've just got this huge numerator divided by, you know, whatever. Okay, but if we're talking like a kajillion divided by 2, it's still really big. It's just big. So anytime you have a really top heavy, okay, top heavy degree, you're just not gonna see anything leveling out at all. It doesn't level out. No horizontal asymptote at all. The graph doesn't level out. So it just has none. You're just allowed to write none if you want to, or no HA if you want to, okay? So horizontal asymptotes are not errors, ladies and gents, they're not errors. What they are is they are the end behavior. You have to imagine what the graph does in the long run. You still indicate with dotted lines, okay? So I would like to see dotted lines drawn when you graph these, but in terms of what they mean something very different. So the horizontal asymptotes are not errors, but they are simply values that the graph approaches in the long run, output values, of course, that the graph approaches. So like when you're graphing one of these bad boys, let me just give you a sense for like what the full expectation would be. So obviously you're allowed to use Desmos, but the expectation would be that you would not only have the entire function drawn in to the best of your ability. So, you know, don't be all sloppy on me here. Do a good job with your graphs. But the other expectation is that you would have every single asymptote drawn in, indicated by a dotted line. So like this right here is what I would expect that graph to look like. You can identify where the intercepts are. We'll talk about that a little bit more in the next video, but you can identify where the intercepts are. Desmos is super user-friendly in that way. So there's no guessing, okay? Please label your axes and do a good job on these. But also I would expect to see your asymptotes drawn in with dotted lines. If you don't have asymptotes drawn in with dotted lines, I'm going to be crabby and I'm not gonna have full points on anything that you turn in if your asymptotes aren't drawn in the right spot, okay? Okay, so that wraps up our conversation on horizontal asymptotes. And hopefully that made sense. If not, you know where to find me, and we will be in touch and talk soon, guys. Thank you for your time.